This question gives us two things. It gives us a frequency of 384 hertz, and it gives us the length of the column where we have a resonant point. So the length is 67.5 centimeters, which is the same as 0.675 meters. But it's a closed pipe. So if we think back to what a wavelength looks like, if I draw a wavelength and I say, okay, there is my full wavelength, I can say, okay, that right there is equal to one wavelength. If I draw the other side of it and draw the standing wave, I would say, okay, there's the other side of my standing wave. For this tube to produce resonance, we know that we have to have the tube ending at an antinode. So the antinode is the place of maximum amplitude, which would be right there or right there. If we have a closed tube, we know that in the closed tube, it is going to be at a fixed point at the end. So we know that the fixed point at the end means that both pieces, or both sides of the standing wave, are going to be attached to the middle. So we know that when we draw our standing wave in our closed tube, we would need it to look something like that, because we would need the antinodes to happen right here on the end of the closed tube. So if we look at where on the wavelength these antinodes are happening, that's a half wavelength right there. So the antinodes are not happening at the half wavelength. You can see that the antinodes are happening right here and here, which would be a quarter wavelength, 3/4 wavelength, and they would happen again at 5/4, 7/4, etc. So because this is a closed tube, I know that my points of resonance would have to happen at 1/4 wavelength, 3/4 wavelength, 5/4 wavelengths, etc. So the first part of the question says, what are the possible wavelengths? So I know that my first possible wavelength is going to be a quarter wavelength is going to equal my length. That's my first case scenario. My second case scenario is going to be that 3/4 of the wavelength is equal to the length of my pipe. And my third case scenario is going to be when I have 4/4 of a wavelength is equal to the length. I could keep going, but I'll just stop here. So first thing I'm going to do here is calculate my possible wavelengths. So I'm going to have to rearrange this for the wavelength. And to do that, I know that my wavelength is going to be 4 times my length. And 4 times my length is going to be 4 times 0.075 meters, which is going to give me a possible wavelength of 2.7 meters. In my second situation, again, I'm going to rearrange. That is going to get me 4 times the length divided by 3 is equal to my wavelength. So I'm going to do 4 times my length divided by 3, and that is going to get me 0.900 meters. And then my third case scenario, I'm going to get that my wavelength is equal to 4 times my length divided by 5, and that is going to give me an answer of 0.540 meters. So these are the 3 possible wavelengths that could be producing resonance, because this is where we would have an antinode at the end of our closed tube. So that's kind of our first part of the question. The second part of the question says, if the speed of sound is about 300 meters per second, what is the actual wavelength and the actual speed of sound in this example? We talked about on the first slide, the actual speed of sound is 343 meters per second. So that's why we're looking for a number that's around 300 meters per second. So basically what we're going to do is we're going to take all of these different wavelengths, we're going to plug them into our universal wave equation and figure out which one gets us closest to the speed of sound. So my formula here is going to be that our speed of sound is equal to our frequency multiplied by our wavelength. So that means we're going to do our frequency, which is 384 hertz, multiplied by our wavelength, which is 2.70 meters. That is going to get me an answer of 1,037 meters per second. So that answer is way, way, way too high, which tells us that it must not be this first point of resonance. Our tube must be longer than that because sound can't possibly go that fast. So we're going to try our second one, which our speed of sound is our frequency times our wavelength. So this means this time we're doing 384 multiplied by 0.9. We are going to get an answer of 345.6 meters per second, which for significant digits we would say 346 meters per second, which is very close to our 343 meters per second. So that is going to be our answer. But just to check, we're going to go on and do our last one, which is our speed equals our frequency times our wavelength. And in this case, we're going to do our 384 multiplied by our 0.54. And here we're going to get an answer of 207 meters per second, which is way too slow. That's much slower than the speed of sound, so it can't be that one, which means that this is our actual speed of sound, and that also means that our actual wavelength is going to be 0.9 meters, and this is the point of resonance. So we were at 3/4 of a wavelength, which if you look up at the diagram that we did initially, that would mean that the tube is ending about here at 3/4 of a wavelength.